So what did we do in the last 4 summers? We flew, and I'm going to talk mostly about the results from the high altitude plane, because my favorite instrument are dropsondes. Of course, I use the radar, but if I have a high altitude plane with the dropsondes, I'm happy. 43 flights in 2020, 1,300 dropsondes dropped, and so on. It's hugely impressive, really. On the pictures here, though, that's the G4, the high altitude plane, and this is the P3. So what do we own? We own in the States 3 high altitude planes between NASA, NOAA, and NCAR. And we have 2 P3s, 2 C-130s, 1 Air Force, 1 NCAR. Long story short, we had 2 P3s, which fly like 3 kilometers, penetrate the hurricane, and they are looking for the low-level vorticity, whereas the G4 flies above the hurricane and drops the dropsondes. Now, we don't want to drop the dropsondes in the worst convection possible, because the lightning will hit the sonde. But what we do is we drop all around, and then we get the environment. So we're not chasing the individual updraft, but we are getting the environment in which the hurricane will develop or not. And we try to do it on a very nice grid so that we can perform, I'm not going to read this, so we can perform the 3D VAR analysis, which is basically analysis that if you have enough dropsondes, you can tell in that area what has really happened in the 3D, and then you can calculate the fluxes. Okay, so some of the predictors, and I can see that there are some people here who heard my talk yesterday, predictors for strong convection, that the environment is favorable, apart from SST and the shear. Saturation fraction, which is a measure of moisture in a vertical column, and the instability index, that you can think about it as low to mid tropospheric moist convective instability, which is the difference between the 2 saturated moist entropies in 2 layers. So the lower level, 1 to 3 kilometers, and 5 to 7 kilometers. And now if your head is spinning, what the heck is saturated moist entropy, and it's been a while, you can think about it as a temperature. It's basically the difference between 2 temperatures averaged in those layers. The instability index tends to be anti-correlated with saturation fraction. And I'm going to show you some results from 2 different field projects. One is OTREC, that Dave, Raymond, and I led in 2019 in the Eastern Pacific and Southwest Caribbean, and PREDICT in 2010, PREDICT targeted hurricanes, whereas OTREC didn't. OTREC studied all types of convection, PREDICT targeted tropical storms and hurricanes. So what we are seeing here in the colored contours is the average moisture convergence, and what we think that that's an excellent proxy for precipitation. So think about it as precipitation. On x-axis, instability index, saturation fraction. On the y-axis, left OTREC, right PREDICT, and I think you can all see that exactly where we have the very high saturation fraction and low instability index is where we are going to get the most rain. Now, this is not the only measure for the convection or the strength of convection, and I'll talk about the vertical mass flux profiles in a bit. But before that, I want to show you this. So this is a plot of OTREC PREDICT instability index versus mid-level vorticity. Mid-level vorticity is extremely important for the hurricanes. And as you can see in OTREC, those two don't correlate. And that's not a surprise, because we flew in tropical storms before they really started to develop, because we were not that interested in studying hurricanes when they are at its strongest. Whereas in PREDICT, there is a nice correlation between mid-level vortex and the instability index. Instability index has to be low for the hurricane to develop. Okay, so I'm now going to go into 4 hurricanes and actually show you what we do and what we process the same day, and then send it to our hurricane research division colleagues. And in that way, we kind of try to know what is going to happen the next day when we fly again. On the left is Hurricane Sally. This is its path, and you can see when it developed into hurricane. And on the bottom is the best track data. So the pressure in red, and in black, the wind speed. In gray here is when we flew with the high altitude plane. So we flew much more with the other plane, but this is when we flew with the high altitude plane. And so you can see in Sally 2, which I will be showing more about, this is exactly when the rapid intensification was happening. So that was when we were in flight. So very excited to see what happened there. Grace, on the other hand, that one, okay. So I'm going to be showing you Grace 2 here. Well, Grace 2 was really dilly-dallying, like was not doing anything. And we hope to see something different in our analysis. So we're going to look at saturation fraction and stability index, but then we're going to look at vorticity and mass fluxes. So first I'm showing you saturation fraction for Sally 2 and Grace 2 in these colored contours. Latitude, longitude. In cyan is the vertical mass flux at certain level. So for Sally 2, the maximum in the vertical mass flux was 4 kilometers. So that's plotted here. And for Grace, it was at 8 kilometers. And we find that out because we plot them at all the levels. And I'll actually show you that for Hurricane Ian. Then what we do, we look at that area where the vertical mass flux profile is the strongest, and we average to see what's going on there. But we also look, okay, so saturation fraction much higher in Sally than in Grace. Let's see instability index. So the same kind of plot. Instability index much lower than for Grace, which remember dilly-dallied, so it wasn't ready. And then in that box, so in this red box, we average and we look at the vorticity. So people used to look at the vorticity at the center, especially at the low-level center, which is ridiculous because you always have vorticity there, and it's not going to tell you much. So what you want to look is, you want to look at vorticity where convection is, because you're trying to pair up vorticity and vorticity tendencies with convection, because convection is the one who is changing it. So you're looking at the area where convection is, and then you're looking at what vorticity does in that area. And so, wow, look at that. Sally 2 has a beautiful mid-level vortex, and Grace does not. What does mid-level vortex mean? So mid-level vortex means if you have that PV anomaly in the mid-levels, what will happen is you're going to get the warmer temperature anomaly above and cooler below via the thermal wind equation. And then if you remember that the instability index is just the difference between two temperatures, what that will do is it's going to lower the instability index. And the low instability index has been known to be connected with bottom-heavy vertical mass flux profile. And so here is Sally 2, and I want you to remember this number, 0.3. This is the magnitude of Sally 2. This is the vertical mass flux profile for Grace, top heavy. So it was just undergoing that cycle, top heavy vertical mass flux profile. So it was decaying, perhaps created later on the mid-level vortex, but we didn't have those flights. This is just to say that I don't just do observations and theory, but we do some kind of modeling. This is the weak temperature gradient model, observations versus the model for the run for Sally 2, which we were very happy to see that it worked out so well. Okay, so I'm going to conclude the first part. Branko, how much time do I have? Conclusions from Sally and Grace. What did we learn? So instability index decreases with increasing mid-level vorticity. The instability index tends to be anti-correlated with saturation fraction. Well, yeah, that was one of the first slides. But instability index and saturation fraction govern the mass flux profile, and mass flux profile then governs the response of the vortex to the convection. Now, I don't have time to show you the vorticity tendencies, but Sally was so not aligned. And vorticity tendencies under the mid-level vortex. So under the mid-level vortex, due to convection, the low-level vortex developed. It didn't kind of like advect to each other. No, it developed under it. That's really cool. So now I'm going to talk, this is kind of like my second part, about Ian. all heard about Ian in 2022. Unfortunately, in the US, I guess it's the same as in Croatia. People still don't believe us. And so they don't evacuate, or they say, oh, I've done so many hurricanes, I can do this one. We've all seen what happened with Otis in October. I mean, that's exactly, that's when we didn't even warn anybody because we didn't know what Otis is going to do. But Hurricane Ian, whose name is retired due to that kind of destruction, had this kind of fast track data. So you can see that it was rapidly intensifying somewhere between the 3rd flight and the 6th flight. You can see that we really put in all the resources. We flew like crazy. And so this is just the high altitude G4 plane flights. There were like at least 2 and sometimes 4 per day of P3 flights, and plus the Air Force. I put in Hurricane Lee. This summer was boring, in my opinion. I ask my students, what's your favorite hurricane? And then sometimes I get the answers like, how can you ask me that? Hurricane Lee was interesting because it was just there as a hurricane forever, and like hit cold water and everything. I was still there. Now we kept flying into it, and we kept flying into it. We kept getting the same kind of, profiles and everything. I'm like, what is going on? At least that Sally was interesting. It was changing. Okay, so Ian, we're going to look at Ian against mass flux, vorticity, etc., and look at the story that Ian tells us. So what do we do first? We look at the absolute vorticity and mass flux, and as we don't know if it's in decaying or growing stage, we look at the mass flux profile everywhere, right? So let's see, 2, 4, 6, and 8 kilometers, and then we find where the maximum was. So this is Ian 2. Ian 1's flight, they didn't drop the drop zones correctly. So here is our little box that we will average in, but we can also look at some other things. So we can look where that box is in relationship to the circulation. So these winds are at 2 kilometers. So that's the low level circulation. We can also look at the vorticity 2, 4, 6, and 8 kilometers. If you look at the latitude and longitude, it's remarkably aligned already, which was nothing like Sally. Sally was nothing of the sort. Ian 2. So Ian 2, this is before rapid intensification. Saturation fraction and stability index in those boxes. And then Ian 6, when it was really an impressive hurricane. My colleagues who flew in Ian just prior to the landfall said that they have never experienced that kind of turbulence. That was the first time that they were actually scared. We can see a very powerful hurricane. Vorticities are very much aligned. The mass flux is strong, but how strong we'll see very soon. Saturation fractions super high, stability index super low. And then the vertical mass flux profiles. And so when I saw that, remember that number that I told you about Sally 2.3? And then I'm looking at Ian, I'm looking at Ian 2, I'm looking at Ian 3, and then we're flying the next day, and then we're flying again, and I'm looking at it, I'm saying, what the heck is going on? How is that thing undergoing rapid intensification if it doesn't have any kind of impressive vertical mass flux? And then, to prove me wrong again, Lee does the same thing. I mean, okay, Lee 10, but really it had so much time to do that. So we're thinking about this for a long time, for a year. And this is what we think might have happened. So in the blue here, I'm showing shear. Let's go back to basics. We say like, okay, let's lay off the SST and the shear, but I guess you can't. In the dashed line is the mean environmental shear for all rapid intensification cases between 82 and 2020. And then in the solid line is the shear that the environment had. And so we can see that in Sally, there was lots of shear. I mean, there is never lots of shear, or we wouldn't have a hurricane, but low to moderate, we call that. Whereas this is Hurricane Ian. Way below average shear. So what I think happened is there are two different regimes. One which is like everything starts out beautiful. You have everything just right. Saturation fraction is high and stability index is low, shear is small, vorticity is aligned, and that thing does not have to work for a living. That thing is just aligned and just exists and lives. And then Sally 2 is completely different picture. Sally 2 had to overcome not such perfect conditions. Sally 2 was really not aligned, right? Sally 2 had to work hard. So it created, I don't know what came first, but cause and causality in our business, but it had to work hard. Ergo, the vertical mass flux profile, magnitude of it was extremely high because the convection had to work in order to create the low-level vortex under the mid-level. Yep, I think, yeah, that's my last slide. And I think I've already said that. Thank you very much. And I'm open for questions.
Thank you for interesting talk. When you talk about shear, are you talking about vertical wind shear or horizontal wind shear?
It's 800 to 200 hectopascal.
Thank you.
This absolute vorticity is like 0.1 kiloseconds order of magnitude. Is it?
I'd say 0.3.
Yeah, it goes to 0.4
maximum,
maximum.
but yeah.
This is like million times of Coriolis parameter what we have it here.
Well, we don't have that there.
Okay, you have you have even smaller, so then it's 10 million times because you have Coriolis parameter 10 to minus 5 inverse seconds, and here you have in kiloseconds. If this is 1 over kiloseconds, so 0.1. Just calculated. This is like 100 inverse seconds. That is way too high. So probably I'm missing something.
I'll check with Stipa for the units, but I'm pretty sure. Well, if we have the units wrong here, we don't in Sally because that's published. Pretty sure somebody would have caught it. Yeah.
So there's like 1,000 seconds. Inverse seconds. If I read it correctly, I'm not sure that I'm reading it correctly. I'm talking about this.
Yeah, I see what you're talking about.
Kiloseconds. Yeah. And Coriolis parameter are
1 over kilo, 1 over. Yeah.
Okay.
Would that make sense?
That solves problem. Yeah. Okay.
I think I managed to leave Zagreb a year before you got here. Branko was never my professor. Or I would be shaking now. I would be like, oh, I forgot basic meteorology. More questions? You're worse than students. Students yesterday had lots of questions. Well, I'm happy to have been here and happy that Branko asked me to come, and I would like to maybe work more with Branko to, medicanes, adrocanes. Those seem interesting. I mean, the physics is a little bit different, but still fun. You could get a plane, fly over Adriatic, do a field campaign in Croatia. All right, thank you.
Well, we promised intercontinental flight. So now we go to West Africa. West Africa is also very much related to generation of hurricanes through easterly waves and so on. And I'm glad to announce that Mr. Asi Yapo, who's also a PhD, will tell us about dry and wet spell.
So, hello everybody. I'm Yapo Marshall, PhD in atmospheric physics, especially in climate and environment, in the Department of Science and Technology of University Alassane Ouattara, Côte d'Ivoire. I'm going to present to you my work entitled Changes in the Seasonal Cycle of Heat Wave, Drought, and the Wet Spell over West Africa using coded simulation. My presentation, first, I will introduce the work. In the second part, I describe the material and method. Then I present some results and discussion, and finally make a conclusion. In introduction, West Africa is one of the most affected regions by the effect of climate change for many reasons. Among these reasons, we have a high vulnerability, a poor economy, and low capacity for adaptation. Consequently, climate change has several societal impacts in many activity sectors, including agriculture, tourism, transportation, infrastructure, economy, and health. Nowadays, we notice the recurrence, the frequency, and intensification of climate extreme events in response to global warming. Among these climate extremes, we have heat wave, dry and wet spell, considered the most dangerous hazard as they have drastic impact on human and natural ecosystem as well as on anthropogenic activities. Few studies have been investigated over West Africa on heat wave and over extreme. But these studies didn't analyze the composite effect of heat wave with over climate extreme. For this study, we aim to provide a comprehensive analysis of heat wave associated with wet and dry spells over West Africa using coded simulation. Specifically, the study will evaluate the strength of coded simulation and the ensemble mean in capturing the seasonal cycle of heat wave and wet and dry spell under present climate conditions, with respect to the observation of climate prediction center. Secondly, this study will analyze the projected changes in the seasonal cycle of heat wave, dry, and wet spell over two future periods. The near future from 2031 to 2060, and the far future period from 2071 to 2100 with respect to the climate condition, which is 1976 to 2005. So, with the material and method, we first present the study domain. The study domain is West Africa, which is localized between the latitude 5 to 15 degree north and the longitude 15 degree west, east to 15 degree east. Our subregion, the West Africa region is subdivided into three subregions. We have the Western Sahel and the East Sahel, which is the Sahelian region. In this region, the climate, the rainfall regime is unimodal. So the peak of rainfall occurs in August, and the mean annual precipitation accumulation is about 400 to 600 millimeters per year. We have the Gulf of Guinea region, which borders along the Gulf of Guinea, the sea. And in this region, we have a bimodal rainfall regime occurring in June and October, and the precipitation accumulation are between 1,500 to 2,000 millimeters per year. West African region climate is mostly influenced by the West African monsoon flux, which govern the rainy season and thus the rain-fed agriculture. In the material and methodology, we have some data. We choose one observation data provided by the Climate Prediction Center and 4 coded simulation. We have a model CIMA, a model, the Swedish model, or ERA model, the CCLM model, and the ensemble mean. We also use daily maximum temperature and precipitation over a horizontal resolution about 0.44 degree. It is about 50 kilometers. This data covers the period from 1950 to 2005, called the historical period, and the period from 2006 to 2100, called the projection period. We also have 2 scenarios of representative concentration pathways. We have the scenario of stabilization, called the RCP 4.5, and the scenario of high emission greenhouse gas emission, which is the RCP 8.5. The method, we calculated the expected climate change and detection indices defined by Alexander and Klein. These indices are 2 types. The indices based precipitation, which are the consecutive dry days. Consecutive dry days have a maximum length of consecutive days which precipitation amount is below 1 millimeter. And the consecutive dry days, the consecutive wet days are the maximum length of days where daily precipitation amount is above 1 millimeter, and the units are in days. The temperature-based indices is the heat wave duration index, which is the number of days over an interval of at least 3 days where the maximum temperature is above the 19th percentile of the maximum temperature, and the unit is also in day. We computed the multi-model ensemble of the 4 simulations using this equation, and then we defined 3 periods: the historical period from 1976 to 2005, and the near future period from 2031 to 2060, and the far future period from 2071 to 2100. And we estimated the climate change signal in percentage using this expression, where projection is the values of the index in the future period, and the reference is the value of the index in the historical period. The result we show in the figure 2, the annual cycle of the consecutive dry days during the historical period. The first figure represents the annual cycle of the consecutive dry days over East Sahel. In the middle, we have this seasonal cycle over West Sahel, and the left figure we have for Guinea Coast region. And the color indicates the different coded climate model. For the seasonal cycle of consecutive dry days, all the model capture well the seasonal cycle of consecutive dry days over the 3 sub-regions of West Africa. And for Sahelian region, we have long dry spell about 30 days from November to March. And over Gulf of Guinea region, we have a long dry spell about 30 days occurring from December to February over the Gulf of Guinea. In figure 3, you present the annual cycle of a consecutive wet days over the 3 sub-regions of West Africa. So for this index, coded simulation capture the seasonal cycle variability over the 3 sub-regions of West Africa. And we have another estimation over this region by all recorded simulation during the period from March to November. This other estimation is caused by the sensitivity of the model to reproduce the humidity flux. In figure 4, we present the annual cycle of heat wave duration index over the 3 subregions of West Africa. So for this index, we have another estimation for all recorded simulation. And the Saharan region represents 3 peaks in January, May, and October, while over Guinea Gulf region, we have 1 peak of heat wave occurring over in April. So the recorded simulation satisfactorily represents the seasonal cycle of heat wave duration index over the period of 1976 to 2005. In figure 5, we represent the validation of the different recorded simulation using the Taylor diagram. The Taylor diagram indicates 3 statistical quantities: the correlation coefficient, the centered root mean square error, and the amplitude of the variation of the different recorded simulation represented by the standard deviation. So for the consecutive dry day index, all recorded simulations have the same standard deviation of the amplitude of variation, but they have different root mean square error with an overestimation of this index over the 3 subregions. For consecutive wet days, the same standard deviation is observed for all recorded simulation, but different root mean square. So all recorded simulation overestimate this index over the 3 subregions of West Africa. In figure 7, we show the validation of the heat wave duration index over the 3 subregions of West Africa. So for this index, the amplitude of variation is well captured by recorded simulation over the eastern and western side. Thus, we have a good reproduction of this index over Saharan region. Otherwise, over Gulf of Guinea, we have an overestimation of this index. In table 3, we represent the summary of a correlation coefficient between the multi-model ensemble, the mean of the 4 recorded simulation, and the observation climate prediction center. For the 3 indices and the 3 subregions of West Africa, we have a good correlation greater than 0.8 between the multi-model ensemble and the climate prediction center referred as the observation data, except over Gulf of Guinea, where the correlation coefficient is small. It is about 0.42. So this situation is due to the fact that over the subregion of Guinea Gulf, we have an overestimation of heat wave duration index by all recorded simulation. In figure 8, we present the projected changes in heat wave duration index under the scenario RCP 4.5 and the RCP 8.5 during the near future period. The figure on the left represents the changes over under the scenario RCP 4.5, and the figure on the right represents the changes over the scenario RCP 8.5. The 2 first figures above represent the changes over the eastern side. The middle figure represents the changes over the western side, and the below figure represents the changes over Gulf of Guinea. So for the heat wave duration index, we have an increase about 10 days of heat wave over all the West Africa region under both scenarios. And this increase may be explained by the possible changes in the dynamic feature of the West African monsoon and the teleconnection with El Nino or ELSO in the context of global warming. So for the coastal region of Guinea Gulf, these changes can be explained by the moisture flux coming from the ocean and the evapotranspiration phenomenon, which will increase the water vapor content in the atmosphere, which induce heat wave. In figure 9, we present the changes in consecutive wet days over the near future period for the three sub-regions of West Africa. For this index, we have a decrease of consecutive wet days over Saharan region during the period from March to November and during the undercycle of the Gulf of Guinea. We also noticed that the CCLA model indicates an important decrease, about 8 days in Saharan region, while an increase about 5 days during September to December in Gulf of Guinea region. This is due to the use of convective scheme used by this model, which is Tilke convective scheme. In figure 10, we present the changes in consecutive dry days under both scenarios over the three sub-regions of West Africa. For the consecutive dry days, we have an increase in general during the period from March to November over the Saharan region, except the Swedish model and Canadian model, which indicate a decrease. So the increase in this index is in general in Gulf of Guinea, except ERA model, which indicates a decrease under the scenario RCP 8.5. We noticed that some discrepancies between the model, which means that there are some uncertainties existing in projected changes in consecutive dry days, while the multi-model ensemble of the four models indicate clearly an increase. So this decreasing consecutive wet days and increasing consecutive dry days period coincide, which could have impacts on rainfall onset over West Africa. In conclusion, the seasonal cycle of heat wave, dry and wet spells in West Africa is well captured by the recorded simulation over the three sub-regions of West Africa. And these biases are characterized by an underestimation about 30% for the consecutive dry days, and an overestimation estimated about 60% and 50% for consecutive wet days and heat wave duration index, respectively. For future projection, we have an increase about 10 to 20 days in heat wave duration over West Africa under both scenarios over the near and the far future period. We have also an increase about 80% in consecutive dry days over West Africa and a decrease about 40% in consecutive wet days. We also have a coincidence of increasing consecutive dry days and decreasing consecutive wet days period in West Africa. So West African countries will be affected by the simultaneous effect of wet and dry spell associated to heat wave. Third, government and stakeholders must take action to suitably reduce greenhouse gas emissions in West Africa. Thank you for your attention.
Thank you, Asiapo. We have time for a couple of questions. I hope that you hear us.
Yes, I hear you.
Okay, while waiting for a question, would you please tell us about the fate, about the future of the summer monsoon in that area? Will they be earlier or later or longer or more intensive?
So monsoon will be intense, and the start of a monsoon will be disturbed by some phenomenon like a dry spell, which can be the monsoon start will be late a bit for the agriculture production.
You have more questions? Okay, if not, then thank you very much, Asiapo, for joining us here in Zagreb, and
Okay,
good
thank
luck
you.
with your research.
Okay, thank you also.
So this is the end of this session, and now we are all of a sudden ahead of time. And the next chairing person is Lydia Srnec. I saw her here today and still here. And let's see if the next presenters are ready. Okay, Ivana is ready. Others. So I have permission from the organizers that we keep on going and that perhaps we finish up earlier.
Thank you, Branko. I have a pleasure to announce the next speaker that recently published this work, as far as I know, together with our Sara and Margareta. So Ivana, the floor is yours.
Good evening. Today I will talk about my favorite topic, which is tropical, extratropical teleconnections, as you know. How many of you here doesn't speak Croatian? Maybe it's a better idea. Okay, then I will continue. Okay, today I will talk about the impact of tropical ocean SSTs on signal over the North Atlantic European region. And this is the work I've done with collaboration with my postdoc student, Sara, and my master student, Margareta, and I'm very thankful for their hard work, and without them, this work wouldn't be published. So let's see, why tropical oceans? We all know that tropical oceans are strong generators of climate variability all over the world because of the stored heat, and they also are physically coupled with atmosphere, and they contribute to the distribution of heat, water, and momentum. And that's why we are interested in tropical oceans. We also know that in tropical Pacific, the very famous phenomenon is ENSO. And it is well known that the neutral situation is connected with quite warm sea surface over here. But during the El Nino, the Eastern Pacific is warmer than usual. And in that case, we have the shift of tropical convection and also the shift of tropical rainfall. During La Nina, the situation is quite similar to the neutral, but the water is much colder here. As a consequence of such very intensive processes, we have the source of Rossby waves. This is the atmospheric Rossby waves, and they emanate in atmosphere above the tropical Pacific, and they propagate toward the mid-latitudes. This is the way how tropical oceans can influence also extratropical, which is quite far from that source of Rossby waves. On the other hand, we are interested in North Atlantic European region, which is associated with very strong internal variability of atmosphere. And there is a quite challenging to isolate signal there because of that strong variability. And we also know that that area is associated with North Atlantic oscillations, and this is the first mode of climate variability there. And weather and climate of our region is dominantly affected with North Atlantic oscillation. So we are interested in this region. We know that the internal variability is very strong here, but we are also interested in impact of tropical oceans from Pacific, Atlantic, Indian Ocean. And we analyzed many experiments to distinguish internal from SST forced variability. And also our goal was to estimate relative contribution of different tropical ocean basins. We used ICTP AGCM, nicknamed Speedy, which is quite easy model to handle with. And it was found that it is very successful in simulating tropical, extratropical teleconnections, and it has been used many times for investigations like this one. And we also used the analysis to check, to compare data with simulated data. Of course, we need to design our experiment, and we did it in such a way. So we used Speedy. We performed 7 ensembles of 35 numerical simulations, which were quite long, 156 years. And here are most of those experiments we used. So we performed global experiment with SST forcing prescribed all over the oceans. We also had a tropical Atlantic experiment with forcing only in tropical Atlantic, tropical Indian Ocean forcing, tropical Pacific in tropical Pacific, and on tropics is the experiment with SST forcing prescribed in the whole tropical belt. And at the end, we also did one more experiment with SST forcing prescribed only in North Atlantic. We also did some other experiments, but I will not show it here. And the CLIM experiment is very important experiment because it is unforced experiment with climatological SSTs prescribed during the whole integration. We also did empirical orthogonal function analysis, which is quite famous technique. We calculated signal according to this equation. And we also separated the whole 156 years into ENSO years, which are associated with quite strong DINO 3.4 index, and non-ENSO years or neutral years. So first, I will show you some results of signal analysis. And here you can see the total signal based on all period. And the first line here is the signal in globe experiment. You can recognize here over the Pacific North American region quite strong triple pattern of anomalies. We know that the signal is really strong there, but we are more interested in this pattern over the North Atlantic, and you may recognize isolated pattern over the North Atlantic. Similar patterns are also found in TROPAC experiment, also in tropics experiment. In tropical Atlantic and tropical Indian Ocean, it's very weak signal there. But if you focus now on the CLIM experiment, which is unforced experiment, you may recognize quite weak signal here. And we were very happy with this experiment because we use it as to test statistical significance of our results. So everywhere where the signal is stronger than this in CLIM run, we can say that the result is statistically significant. Now you can see here the ENSO signal based on 53 years, and you may recognize particularly in globe run that the signal is much stronger over the America, but also here over the North Atlantic. Over the tropical Atlantic and tropical Indian Ocean, in these experiments, the signal is almost the same as here, but in TROPAC and tropics, we can recognize that over the not only over the North American, but also over the North Atlantic region, the signal has been strengthened. Of course, in CLIM run, there is no change in the signal as expected because that is unforced run. Non-ENSO signal is much weaker than those two, but you may recognize here that still we have something in all experiments. So that means that feature over the North Atlantic exists independently of SST forcing, but it is obviously increased by SST forcing, as you can see in those SST forced runs. So if we compare TROPAC and the tropics signal during the ENSO years, you may recognize that for TROPAC run, the signal is stronger than in tropics, which is an indication of competitive influences of individual tropical basins. On the other hand, if you compare those results over the North Atlantic with signal for globe run, you may see that here the signals are stronger than in this tropics run, which means that something from extratropics actually strengthened the signal over the North Atlantic. Okay. So this amplifying influence of extratropical ocean is a quite new result according to existing literature. We also performed the North Atlantic run with, if you remember the first slide I showed you, it is the run with SST forcing prescribed only in North Atlantic. And we used also the signal for ENSO years. So in that way, we, in some indirect way, accept that there was some forcing from ENSO coming to extratropical Atlantic and producing SST anomalies there. And you may recognize here over the North Atlantic, there is a signal. So obviously North Atlantic has a contribution to signal over the North Atlantic European region. So signal comes from the tropical Pacific through the atmosphere and induce some SST anomalies in North Atlantic, and those SSTs in North Atlantic enhance the signal in atmosphere. We also looked at the reanalysis data just to check if there is some, maybe it could be some model artifact. And we look at the ENSO events, but to exclude natural variability, we looked only NO neutral events because NO is consequences of internal variability of atmosphere, and in fact, it acts as a noise. So we did the, we calculated geopotential height 200 hectopascals variance based on reanalysis for neutral years for all investigated period, ENSO and non-ENSO years. And you may recognize here, and by comparison of these results, that ENSO years are much stronger signal here over the North Atlantic than during the ENSO neutral years, which is an indication that we can recognize ENSO impact in reanalysis as well. If you compare reanalysis data with modeling data, you may recognize that the patterns are quite similar, particularly over the North Atlantic, which means that the speedy model and reanalysis have more or less similar results. We also performed EOF analysis because we wanted to extract internal variability, which is associated with EOF analysis performed to all members, and also to isolate SST forced variability, which is associated with ensemble mean. And on data, we obtained these results for globe run, CHOPAC run, and CLIM run. When we do EOFs using all members of our model, the results are quite similar. And maybe you can recognize here NO pattern, which is more or less the first mode of EOF. So all three runs have similar pattern when we use all members. But when we do EOF analysis on ensemble mean, then globe run and CHOPAC run are quite similar with this strong monopole pattern over the North Atlantic European region. But CLIM run is very different, which is expected because CLIM run is not forced run, and ensemble mean should reflect SST forced component of climate variability. So if we compare the signal calculated to that equation I showed you before and EOF analysis for globe and CHOPAC run, you may see here the similarity not only over the Pacific North American region, but also over the North Atlantic, which means that ENSO signal is reflected in first EOF of ensemble mean in SST forced component. Here you can see that NO pattern is dipole, but this pattern over the North Atlantic in both simulated and reanalysis data are much more similar to Eastern Atlantic pattern, which is quite new perspective of ENSO impact on the North Atlantic European region, because we concluded at the end that this signal actually projects onto Eastern Atlantic pattern. At the end, we can conclude some points here. So SST boundary forcing, especially in tropical Pacific is important for signal over the North Atlantic European region. The same pattern exists in unforced run, but it is enhanced by SST forcing in tropical Pacific. We also confirmed that the similar pattern is found in the analysis. And we also found some competitive influence from different tropical bases. And at the end, we can look at the response, atmospheric response to ENSO forcing over the North Atlantic European region in a similar way as Molteni and Palmer proposed for a PNA region, as locking of the chaotic extratropical circulation into one of its regimes, but here that regime is East Atlantic pattern. We also find some impact on storm tracks and so on, but for more details, I suggest you to read our recently published paper. And you can ask me, of course, questions.
Thank you, Ivana. Do you have some question from public?
Everything is clear. Thank you.
If not, Ivana, can you tell us what we can expect regarding ENSO? El Niño developed this
In future or now? We
Now,
know that El Niño-
this winter.
Yeah. El Niño is quite strong and developing in tropical Pacific. And we can expect extreme weathers and associated with. So I think that a lot of you been last week on.
Yeah.
Yeah,
I was
so there
listening
was a
and I
talk,
hope we
yes,
will not
by
have
Mike.
severe weather.
Yeah, yeah.
Yes. Okay, thank you. And now from teleconnection, we came to synoptic scale. Ivana will tell us how she's working on weather types, synoptic weather types. So let us see.
Dobar dan svima. Hvala što ste ostali do samog kraja nakon ovako bogatog današnjeg programa. Ja ću pričati na hrvatski, čisto malo radi ravnotežu sekcije. Slajdovi će biti na engleskim, tako da svi mogu pratiti. Ja ću vam danas dati jedan pregled svog doktorskog istraživanja i neke dobivene rezultate. Mislim da ne moram posebno objašnjavati klimatsku raznolikost Hrvatske. Vidimo kako se srednja godišnja količina oborine podudara sa topografijom, što ukazuje kako lokalni faktori itekako utječu na intenzitet i količinu i učestalost oborine u pojedinim predjelima, što znači da tijekom određene vremenske cirkulacije možemo imati različito vrijeme u pojedinim regijama. Do sada su u Hrvatskoj u kontekstu tipova vremena korištena je samo subjektivna klasifikacija po boji, koja se sastoji od 29 tipova vremena. Oni su određivani za svaki dan, za svaku regiju pojedinačno, a ukupno je 5 regija i to na temelju raspodjele prizemnog tlaka. I to se radilo po ovoj tu shemi. I onda je motivacija za ovaj rad bila da se unaprijede dosadašnja znanja i praksa i da se dobije automatizirani proces klasifikacije tipova vremena koji će imati manje tipova nego pojna klasifikacija i koja će za cijelu Hrvatsku imati jedan tip za svaki dan. A da bi dobili klasifikaciju koja bi najbolje uhvatila varijabilnost oborine u Hrvatskoj, odlučili smo primijeniti rezultate KOST projekta i to prvo katalog, a onda iz dobivenih rezultata i zaključaka pokretali smo software. KOST projekt je osmišljen sa ciljem da se objedini svo znanje Europe vezano za klasifikacije tipova vremena i da se nađe jedna koja će biti zajednička za svih. I zato su svi koristili dnevne ERA40 podatke kao ulazni parametre i definirano je 12 domena u cijeloj Hrvatskoj, a Hrvatska je u cijeloj Europi, a Hrvatska je dio u dvije domene. Domeni 6 to je Alpska regija i domeni 10 koja se odnosi na središnje Sredozemlje. Ovdje je lista metoda koji su korištene. Imamo 4 grupe metoda i ukupno je 14 metoda, a ovdje su također navedene neki od parametara koji su bili dostupni u KOST katalogu. Osim kataloga korišteni su i dnevni podaci oborine sa klimatoloških i kišomjernih postaja DHMZ-a. Ono što je bilo bitno je uskladiti vrijeme podataka ERA 40 sa dnevnim podacima oborine, jer recimo ako uzimamo za jučerašnji dan u 12 UTC ERA 40 podatke, onda su im bliže podaci oborine koji smo izmjerili jutros, ali ja sam im onda predijelila jučerašnji datum i rezultati su onda bili puno bolji. A oborina je uzeta zato što je ona nekako najizazovnija meteorološka varijabla i jako je promjenjiva u prostoru i vremenu. Iako se prema Gajić, Čapka i suradnici Hrvatska dijeli u 7 regija prema oborinskim režimima, već prvi rezultati su pokazali kako u kontekstu klasifikacije tipova vremena je puno primjerenije koristiti regionalizaciju koja je korištena kod pojine klasifikacije, a ona se sastoji od 5 regija. To je istočna i središnja Hrvatska, sjeverni, središnji i južni Jadran. A ove različite boje su regije po Gajić, Čapka. Kako bi prikazali uspješnost pojedine klasifikacije, koriste se različite statističke mjere. U analizi sam koristila 4, pri čemu prva i četvrta pri izračunu uzimaju intenzitet oborine, dok druga i treća mjera uzimaju pojavnost oborine, odnosno premašivanje određenog praga, a ovdje će biti rezultati prikazani samo za ovu mjeru. Postojale su dakle različite opcije koje smo imali na raspolaganju, a u današnjem izlaganju ću se fokusirati na domenu 10, dakle središnje Sredozemlje, jer su rezultati za nju bili bolji od ove za Alpsku regiju. Isto tako kao ciljana varijabla uzeta je oborina, kako sam i prije rekla, i gledano je za različite pragove. Promatrala sam isto klasifikacije po različitim sezonama, a od klasifikacija su uzimane samo one koji su za ulaznu varijablu uzimali tlak, a nisu imali dodatne varijable, i to je prikazano za explained binary variance. Na ovoj tu prvom grafu možemo vidjeti ovisnost izabrane statističke mjere o premašenim pragovima oborine, i ovdje je prikazano dakle 14 klasifikacijskih metoda. Različite boje označavaju različitu grupu metoda i možemo vidjeti kako sa porastom praga se smanjuje statistička mjera, što znači da klasifikacija je manje uspješna za što je oborina ekstremnija. Nadalje možemo vidjeti kako su klasifikacije puno uspješnije na Jadranu nego u kontinentalnoj Hrvatskoj, a slično je vidljivo i na ovom tu grafu koji pokazuje ovisnost o sezonama. Tu vidimo kako odnos uspješnosti klasifikacije u jeseni i u zimi se razlikuje među regijama, dok je za ljeto u svim regijama su klasifikacije najmanje uspješne, što je posljedica konvektivnih oborina ljeti koje klasifikacijske metode ne hvataju. I ovo su neki od zaključaka koje sam spomenula na prethodnim slajdovima. Ali ono što bi još istakla je dakle ta važnost da podaci budu vremenski usklađeni, i isto koliko je bitno u koji položaj ima Hrvatska unutar domene koja se promatra. Ovi dobiveni rezultati su nam onda pomogli i dali nekakve smjernice za pokretanje softvera. Izabrali smo dvije metode iz dvije grupe metoda koji su se pokazale nekako najuspješnijima. Definirali smo 28 domena koji su imale vrlo male razlike. Pokretali smo software za 6 različitih ulaznih varijabli, dakle uz prizemni tlak još ovih 5 i to za različite nivoe i sa različitim težinama smo uzimali pojedine varijable. Korištena je ERA5 set podataka, neki su bili u izvornom obliku, neki su bili izmanipulirani. Također smo se dakle fokusirali na oborinu i za različite pragove. Varirali smo i broj tipova vremena kao i sezone. Kad uzimamo za ulazni parametar relativnu vlažnost i vrtložnost, izgleda na 850 hektopaskala, izgleda da su klasifikacije najuspješnije na ovoj domeni 9, to je mala domena, dok je za ulazni parametar prizemni tlak bolja ova srednja, dakle nešto malo veća domena. A cijela situacija za ovaj tip je prikazana na još većoj domeni. Relativna vlažnost, podaci relativne vlažnosti, kod njih je uklonjen godišnji hod, dok je kod podataka vrtložnosti i prizemnog tlaka oni su standardizirani. Prije sam spomenula da sam ulazne varijable uzimala sa različitim težinama. Rezultati nisu bili jednoznačni i nijedna se klasifikacija kombinacija nije pokazala najboljom. Zapravo je bilo više njih i trebalo izabrati neke koji su najčešće bile najuspješnije. Tako sam se ja odlučila za ove dvije, da sad ne idem u detalje. Uglavnom tu su prikazane centroide za te dvije klasifikacije za 20 tipova. Vidimo da su one međusobno dosta slične, s tim da imaju nekakvih razlika i tu struka pomaže sa svojim iskustvom i kaže da su ovi lijevi puno realniji. Od ove lijeve klasifikacije sam izabrala 2 tipa. I tu sam prikazala na 2 različite domene. Zašto sam uzela baš ova 2? Zato što oba imaju statistički značajan trend oko 1 dan u 10 godina i to gornji ima negativan trend, a donji ima pozitivan trend. Gornji tip je učestaliji u zimskim mjesecima i vlažanje, dok je donji tip učestaliji ljeti i sušije, i pogotovo u istočnoj Hrvatskoj. I ovakvi su rezultati u slaganju sa našim prethodnim istraživanjima koji pokazuju da dolazi do porasta sušnih razdoblja u zimi i ljeti. I zaključak. Dakle, nadali smo se da će nam rezultati iz prvog dijela analize gdje smo primijenili katalog dati dobre smjernice za dalje. Međutim, i dalje je ostalo bez pretjerivanja milijun mogućih opcija koje smo mogli provrtiti i jednostavno je bilo nemoguće svih provrtiti i testirati i zato je bio veliki izazov odrediti koju ćemo parametar prvi fiksirati, s njime nastaviti ili koju ćemo kombinaciju izabrati i onda s njom nastaviti. A opet smo svo vrijeme htjeli zadržati na umu da klasifikacija bude jednostavna, lako primjenjiva i da ima fizikalnog smisla. Također neki od problema su bile klasifikacije koje su bile lažno dobre jer su pojedini tipovi bili prazni. I ova cijela analiza je ukazala da ne postoji nijedna kombinacija koja bi baš pokazivala jasan smjer poboljšanja i da ne postoji savršena klasifikacija. Ima zapravo više njih, a na nama je da onda i temeljem iskustva i onim što nam je prioritet u našem istraživanju izaberemo neku od njih. Sljedeći koraci su da se poslože sve ove kombinacije, da se finaliziraju parametri i da eto dobijemo konačno jednu automatiziranu klasifikaciju tipova vremena za Hrvatsku i u skladu s tim da bi se napravila i baza podataka tipova vremena. Također je plan detaljno analizirati svaki od tih tipova, vidjeti kakvi su trendovi pojedinog tipa, relativna frekvencija, a i kakav tip donosi kakvo vrijeme u koju regiju. Planiramo također primijeniti klasifikaciju u različita područja istraživanja i prakse, a posebno povezati sa sušnim razdobljima i sušom, ekstremnom oborinom, mrazom, toplinskim valovima, biometeorologijom i tako dalje. Evo, to bi bilo sve. Hvala.
Hvala. Zanima me samo u drugom dijelu kad ste upotrebili ovo ERA5 i baš izvrtili stvari. Nisam shvatio po kojem ste kriteriju određivali da je nešto uspješno ili nije između ovih gross weather type i ove druge koju ste koristili.
Znači, računala sam statističke mjere, explain binary variance, Breuer's score i slično, a koristila sam podatke s postaja. I onda sam gledala koliko je koja uspješna bila, koliko je vrijednost. Da, sve zaoboreno. Da, je. Ma prvi dio sam radila i sa tlagom i sa temperaturom, ali fokus je nekako bio na oborene.
Ste spomenuli da kad je oborina ekstremna, da nijedan od ne znam čega ne daje dobre rezultate. Što to znači? Da ekstremna oborina se može pojaviti u bilo kojim uvjetima, u bilo kojoj klasifikaciji ili je to nešto drugo značilo?
Ne, nego da dinamika velike skale loše opisuje ekstremnu oborinu.
Onda sam dobro shvatila. Znači zapravo sinoptička skala nema veze, ekstremna oborina se može pojaviti u bilo kojem sinoptičkim uvjetima.
Da. I to je zapravo za sve metode je bilo isto. Bar je to nešto jednoznačno.
To mi je logično, onda sam dobro shvatila. Hvala.
Hvala i mi željno iščekujemo završetak ove metode jer će nam sigurno biti jako primjenjiva. A sad sljedeća dva predavanja su naše kolege iz Slovenije. Znači s jedne interkonekcije, telekonekcije i sinoptičke skale dolazimo na podatke. Svi znamo koliko su naša mjerenja važna. Tako da će nam kolegica Mateja Nadbat pričati o data recovery and rescue of national climate observation in the Republic of Slovenia.
Good evening. I'm very glad that I can speak about data rescue and recovery of climate data. I've been working on this field for about 10 years, and this would be a short presentation of our achievement. Instead of introduction, I will talk about motivation for this rescuing and recovering of climate data. Afterwards, in the achievement, I will speak about things and work we've managed to accomplish. And in the lessons learned, I will list the final and the most important facts that we found. So, doesn't work, or okay. Motivation. The first motivation is a long-term time series of data. We need this data for numerous climate analysis for the climate change we are facing today. The second motivation is preservation of observed data for future generations, because these reports, as the picture is there, shows that some of the reports are already decaying or bleached, and it's high time to rescue them. So, and the third is European and national legislation on archiving. It's very important fact. And also World Meteorological Organization pay attention to rescuing and recovering of historic data. So its guidelines and initiatives are also the important facts or that motivate us to do this work. In the achievements, I would like to say that according to World Meteorological Organization and its guidelines, there are several steps in rescuing the data. So the first is inventorying, the second one is imaging the data, the third one is keying the data, imaging the documents, the third one is keying the data, and the last one is archiving documents and data. So in the field of inventorying, we managed to inventory all the logbooks and reports in ARSO archive, as well as in foreign archives, because due to Slovenian history, we have a lot of reports or logbooks scattered in foreign archives, such as, for instance, in Italy, Austria. Some are, we suppose that they are also in Hungary and in Serbia. Good source of information for that old historical reports that are stored in foreign archives are historical yearbooks, such as Jahrbucher or a Bollettino Annuale, and so on. We also, in the step of inventorying, we also counted the pages of data or reports in ARSO archives, and there are almost 3 million pages of reports from 1850 to 2020. In this number, it's not included all documents related to metadata or diagrams or so on. This is only 3 million pages of climate reports and precipitation reports. The next step is the imaging of documents. In our archives, the imaging of metadata is in process. It's done by students. All logbooks and reports, climatological and precipitation reports, will be done by professionals in next year, in 2024 and in 2025. But all reports in foreign archives are already imaged. We found a lot of reports in Archive of Geosphere, former ZAMK in Vienna. These reports are from period from 1849 to 1918. And a lot of reports we found also in Archive in Ispra, in Venice. These reports belong to the period of 1918 to 1953. These are already imaged. The third step is keying. From the imaged document, we should key the data. And climate data from 1950 till nowadays are already keyed, quality controlled, and stored in database. They are also it is also available available on the ARSO webpage. Keying the metadata is in process. They are also important. So we do it, but not so efficient as climate data. But climate data before year 1950, only for selected stations are keyed, or for the selected periods of time or selected climate event, the climate data are keyed, Sorry. When we have all these steps done, then is archiving there. This is the last step. The last step, and the paper documents in ARSO archives that are stored in ARSO archives, we would like to transfer them into the national archives, but this would be done after all the reports would be imaged. So this process, or this would be done after the 2025. Digital data are in ARSO database, and all digital documents would be must be in the document database also, but we should create this database. We don't have it. After this, we would image, and the digital documents and data would be also transferred to national archives. ARSO need to, according to national legislation on archives, ARSO need also 2 additional locations for distant locations for backups of digital documents. Lessons learned. This is at the end. So recovering observed data from foreign archives is for Slovenia an important fact, because, due to its turbulent history. We found some data also in historical literature and newspapers. Rescuing observed data is high time, because we didn't find all logbooks and reports. Some of them we think that are lost. Some found reports are already bleached or damaged, so it's really high time to rescue them. Along with the data, we should also rescue metadata, because metadata, historical metadata, can describe all the facts in which the data were observed. So we can critically evaluate the data for its use. So metadata must be also rescued and rescued along with the data, climate data. If we think only for the historical data, then we should follow the World Meteorological Guidelines on best practices for climate data rescue. But we should also think on the current climate data and all other meteorological data we collect nowadays, because sometimes in the future it will be also the historical ones. So the digital data, historical or current data, should be managed with great care and knowledge. And there is a help of legislation, as for instance, there is ISO standard 15489 on European level. and national legislation on archiving. This legislation and guidelines help us to manage the data properly. This is the picture from one of our archive chamber. It tells us that archives there is not only climate data, and there are also metadata as important as climate data. And there's a picture of a lady who is an observer of our precipitation station. An effort and enthusiasm of these observers and money invested in meteorological observations are good reasons for our admiration, respect, and pride. And climate data are cultural heritage, and it would be very irresponsible not to preserve our legacy for the future generations. Thank you.
Thank you, Matea, for very nice presentation. Do we have questions from public? Vesna, please.
Do you rescue or archive only meteorological data or also hydrological and others historical data you have in Slovenia?
Yes. Our colleague in the hydrology, they do this work. I don't know where they are on this field, but they are doing on also this. But
do they use the same method and the same practice as you do for meteorological data, or?
They should do this, but this involves a lot of the staff, there's not so, and there's a lack of money, and there's a lot of problem. There's a problem on this field.
Yeah.
So we would like to do and to perform it properly on the whole ARSO. That includes seismology as well as hydrology and meteorology, and it's important because everything is invested by money of government, our budget, and it would be done properly.
Yeah, thank you.
Yes.
Andrea would like to comment something or ask?
Yeah, thank you, Matea, for this. Just to complement and regarding to the question which was addressed by you, yeah, we will probably implement or somehow empower this work or speed up this work with a Cohesion project. Actually, we received recently confirmation of Cohesion project, which is related to digitalization, and probably we will somehow help to do this work, which Matea presented to you in, let us say, shorter time and with more manpower, which is needed for this kind of work.
So I was searching on your website some climatological data, and I could find only for the 15 main stations. Is there something else to find? What I'm missing?
We have a digital archive on our page. So if you are interested, please send me an email and I will send you the link on our webpage.
Yeah.
There are all meteorological stations, automatic ones, synoptic, climatological, and precipitation stations with data from 1950 onwards.
Okay, once again, thank you very much. I really like the way how you highlight how metadata are important, because anyone who deals with data knows that, for example, the next lecture will speak about homogenization. If you don't know about metadata, it's very hard work. So in next talk, homogenization and interpolation of daily precipitation time series, from Slovenia meteorological station in the period of 1950 to 2020. We will see how they do this.
Croatia, good evening, everybody. Today I'm going to present homogenization and interpolation of daily and monthly precipitation time series from Slovenia in the period of 1950 to 2020. Our last homogenization and interpolation of climate series covers period from 1950 to 2020, and it is is our second homogenization, which is a follow-up from homogenization of our data from the period of 1961 to 2011. Today, I will concentrate on our precipitation time series. I will explain something about our methodology, how we homogenize from monthly data series, how we interpolated daily data, and how we perform this homogenization adjustment to our daily precipitation data. And then I will show you some analysis on long-term trends of precipitation and some comparison with ERA 5 analysis. At the end, I will sum up this. So, how our homogenization was performed on monthly and daily time series of measured daily precipitation data from 2068 stations, 2,200. I'm sorry, 268 stations. 256 were from Slovenia. We have 7 stations from Croatia and 5 from Austria. We were dealing mostly with manual measurements from Hellman rain gauge. We also have many automatic weather stations in last decade, but at least in Slovenia, this data is less reliable. At the beginning, we repeated or done additional quality control. Especially we were concentrated on not on okay, I will come to this later. We've done we are doing operative quality control daily. But we also done some there's blockage. Okay. Then some quality control series from nearby stations were merged into a joint series. This was done. The series were climate similar, and if this was possible, so we prolonged our series, and we calculated monthly sums from daily data, and these monthly sums went into homogenization if calculated missing data precipitation sums were less than half of sums from measured precipitation. So homogenization was done on monthly data with Homer homogenization tool. This is a tool which can be used also interactively, and which make possible usage of metadata like station location, instrument type, changes in stations, changes in instruments, and in people. Then we've done several iterations of this detection of breakpoints, from more obvious and greater to less obvious breakpoints. We compared station series with series from nearest stations as reference stations, and we've used seasonally uniform corrections of this time series. But for 10 stations, especially in winter times, we further manually corrected this series because there was additional and obvious signal sign in these break sizes. And for 3 mountain stations, we have not much mountain stations. So because of lack of appropriate reference stations, we've done homogenization separately and manually. So this is a map with locations of station at the time of our homogenization. We can see 7 stations also from Croatia. And the density of stations is approximately 1 station per 80 square kilometers. And now I will tell you something about the summary of our homogenization. So we had around 1 break per time series on average, and we could verify around 60% these breakpoints by metadata. So there were something on these stations that caused this breakpoint and could be verified. Here on the graph, we can see in green mean correction value through time and its standard deviation. And we can see that these mean values are very small, mostly under 0.5 millimeters. That means that almost that we have evenly distributed magnitude of breaks. So similar breaks in positive and negative side. And around 30% of breaks were larger than 10% of measurements, and maximum size break was 26%. So mean correction on whole network was very small, so there was little change in overall temporal trend on national level after this homogenization. And also this software Homer filled missing values for months, but we weren't satisfied with that, so we later replaced this interpolated data with interpolations from the daily series. So next step was interpolation of daily data, because we also wanted to have homogenized daily values, and we also have to populate this time periods without data. So we used here our own interpolation scheme based on some kind of regression. So for every station we have chosen reference or predictor stations which were chosen by time series correlation. So the higher correlation, higher correlated stations were chosen as a reference predictor. So for every station, then we did linear regression separately for each pair of reference station and station that matters. And then we took interpolated value as weighted sum of these regression values with this weight correlation, which depends on correlation coefficient. And next step was adjustment of distribution of these interpolated values, because due to regression and this weighted sum, distribution of interpolated values differed from distribution of measured values. It was variance was smaller, so we have done some adjustments and applied these adjustments to every interpolated value. And at the end, at final, we had measured and the quality control values corrected by monthly homogenization corrections, plus this adjusted interpolated value. So we had 71 years of data, daily data with no missing values. And we achieved with this a good balance between root mean square error and statistical error in extreme percentiles. And our data is now used for both for climate normals calculations and for extreme values analysis, and also for all climate change analysis in recent decades. But we have to have in mind that some daily values may still be far from true values, and we must not forget this. So next step, I will show you some analysis done on this set. For example, the maps shows long-term trends on annual level and summer for summer period precipitation sums. This was done with this is relative trend, so on precipitation indices, done with tail send method, and larger dots shows statistically significant trends at the level of 5%. Statistical test was Mann-Kendall, I think, and we can see that in annual trend, most at the annual level, most trends are less than 1% in magnitude, and almost all, except maybe one or two, are statistically insignificant. This is for the period from 1950 to 2020. Larger trend can be seen in summer. It is downward trend, this with orange or brown color, mostly on in Western and South Slovenia, up to minus 6% per decade. So trends for other seasons are mostly insignificant. And then some results for extremes, trends in extreme 1-day and 2-day rainfall. This was done with fitting data to non-stationary generalized extreme value distribution. Blue dots are negative, red positive trends, and we can see that for 1-day rainfall, we have mostly insignificant trends, except for a few. It is more, it is less spatially homogeneous, and for 2-day precipitation extremes, we have more statistically significant trends, especially in Western Slovenia. They're up to, I don't know, 10 millimeters per decade. So at last, our data set, homogenized data set, was also used as input data into spatial interpolation on monthly basis from the year of 1950. And we've done some comparison with, of this spatially interpolated data with ERA 5 analysis. We've done comparison of 3.3 half-degree area means, which corresponds to cell areas in ERA 5. So we have Western, Central, and Eastern region. And we can see significant differences between the data set in monthly means. I will show this on the next page. The lowest correlation was in for summer, around 0.5 to 0.6, and there are some significantly different seasonal trends. And this is the graph for monthly means in the period from 1991 to 2020. In blue for Western region, green Central region, and Eastern region. We can see much less precipitation ERA 5 set than in our set, then weaker autumn peak here for ERA 5 data, and also there is less seasonal variation in ERA 5 set than in our data set. Yes. And this is table with calculated trends in precipitation on left side for our homogenized set and on the right side for ERA 5, and with both values correspond to statistically significant differences between these two sets. So we can see that precipitation trends in both sets are quite small and mostly insignificant, but that the differences between the sets are sometimes significant, especially here in summer, where we can also see that the trend difference is increased towards east. And together with low correlation coefficient, we see that there is possibly inhomogeneity in one of these sets. We think that this is an ERA 5 set. And this is, I'm at conclusions. So preparation of precipitation time series is very time consuming. It took us 2 years, I think, or maybe more. Our homogenization in future could be done better by using precipitation type and seasonality cycle. We used one simple method for missing data interpolation, but it proved to be quite good. And our resulting time series show good spatial consistency, especially in long-term trends. And there are some important differences with ERA 5 reanalysis data. So which is also consistent with the literature. So we should maybe be careful using ERA 5 reanalysis, especially in analyzing maybe long trends. And that's all. Thank you for your attention.
Thanks a lot. I was just wondering, you mentioned in your monthly data that you had some issues with mountain stations that you couldn't actually homogenize in a usual way. But knowing the geography of Slovenia, which is quite mountainous, especially in its northern part, I'm just wondering, how did you deal with other mountainous stations, and did you have to do all of them in a different special way manually, or could you only 3 in mountains, everything else is in flat terrain? Okay.
2,000 meters, and then Krvavec around 1,500, and then another one, Zvogel or Kanin. Yes, only 3 stations. Yes, very high, which are different from all what's lower.
I was looking the data of Kredarica station, and if I can remember, there was a really large disparity between the data of precipitation on the station and data on the precipitation map that was made. So when I seen that precipitation field like map, it was more than 3,000 millimeters a year, and on the very station it was only 2,000. So I don't know what's the reason.
So it's lower on our station?
Yeah, then in the interpolation, yes.
Is this really true?
Yeah, I can show you.
Okay. I wouldn't know the reason now, but I don't know. I should check this. But you should be aware that at this station there are many. We don't catch all rain in our gauges because the winds. It's not. Yes.
I know. At least roughly what's happening on this place. Yeah, so that's why I'm interested.
Let us thank the last speaker, but also all speakers in the last section.